Hello and welcome. Today, we're cracking open the chemistry's toolkit. We're going to explore how we build some of the simplest but most fundamental molecules in all of organic chemistry, the alkanes. So let's just dive right in. This is the question that's really at the heart of chemistry. How do you build a molecule from the ground up? Well, I can tell you it's not magic. It's all about strategy, a bit of logic, and most importantly, knowing you have the right tool for the right job. And today, we're going to see exactly what those tools are for building those essential carbon backbones. So what is it we're actually building? Alkanes. These are the simplest family of hydrocarbons, made of just carbon and hydrogen atoms held together by single bonds. And because of that simple, sturdy structure, they're actually pretty non-reactive. Chemists sometimes say they have little affinity for other molecules, which is just a fancy way of saying they don't like to react. And that's what makes them such a stable foundation for building bigger, more complex stuff. Okay, so here's our game plan. We'll kick things off with the most direct way to make alkanes. Then we'll get into some more versatile tools that let us really build and shape carbon chains. And finally, we'll wrap up by figuring out how you choose the perfect reaction for whatever you're trying to build. First up in our toolkit is a method that's, well, all about addition. Let's say you've got a molecule that has some double or triple bonds, what we call an alkene or an alkyne. The most straightforward way to turn that into an alkane is to just add some hydrogen. This process, it's called catalytic hydrogenation. You take your unsaturated molecule, you bubble in some hydrogen gas, and then you use a special metal catalyst, think nickel, platinum, or palladium, to really get the reaction going. What happens is that double or treble bond breaks open, hydrogen atoms snap into place, and poof, just like that, you've got yourself a fully saturated alkane. But let's zoom in a little closer, because the way this happens is actually really cool. This is not a random process at all. Because the reaction takes place on the solid surface of that metal catalyst, both hydrogen atoms get delivered to the exact same side of the molecule. We call this syn addition, and it's a super important detail that chemists use to control the final 3D shape of their product. So really, it all comes down to this neat little three-step dance. First, the alkene molecule kind of lands and sticks onto the metal surface. Then, the catalyst delivers those hydrogen atoms, both to the same side, that's syn orientation. And finally, the brand new alkane just floats away, leaving the catalyst totally free and ready for the next molecule. Pretty efficient, right? All right, so hydrogenation is great, but what if you need to build a carbon chain from scratch? Or what if you want to connect two separate pieces together? For that, you're going to need a more versatile set of tools. So let's see how we can use things called alkyl halides to do just that. Let me introduce you to the Wurtz reaction. This is a classic method for what we call an ascensive chain, which basically just means you're making the carbon chain longer. You take two alkyl halides, you throw in some sodium metal and dry ether, and you basically glue them together to make a new, longer alkane. It's a really powerful tool. But every tool has its limits. The Wurtz reaction is fantastic if you want to combine two identical pieces to make a nice symmetrical alkane with an even number of carbons. But if you try to mix two different alkyl halides to make an odd-numbered chain, you get a total mess. A whole bunch of different products and a really, really poor yield. So definitely not the right tool for every job. So how do we solve that problem? Well, we reach for a more precise instrument. This is the Corey house synthesis. This reaction uses a special little guy called a Gilman reagent. It lets a chemist cleanly connect two different alkyl groups, which makes it the absolute perfect choice for building those tricky asymmetrical alkanes, including the ones with an odd number of carbons. So you see, the choice is totally strategic. Are you trying to build a simple, symmetrical molecule like butane from two ethyl groups? The Wurtz reaction is your friend. But if you need to build something a little more complex, something unsymmetrical like propane, you're going to want the precision of the Corey house synthesis. And hey, just to round out this section of the toolkit, we've also got the Grignard reagent. This is another incredibly useful compound. The moment it comes into contact with anything that has what's called an active hydrogen, like water, for example, it will immediately snatch that hydrogen to form an alkane. It's just another great option to have in your back pocket. Okay, let's switch gears. What if your starting material isn't an alkene or an alkyl halide? What if it's something that has oxygen in it, like a carboxylic acid or a ketone? Well, our next set of tools is all about one thing: deoxygenation, or getting rid of that oxygen. So when we start with carboxylic acids, we've got two main ways to remove that COO group. Kolbe's electrolysis. It's a lot like the Wurtz reaction, actually. It couples two molecules together to create a longer, symmetrical alkane.
The soda-lime process, though, does the opposite. It's what we call a dissentive chain. It just kicks off the carboxyl group, leaving you with an alkane that's one carbon shorter.
Now, what about aldehydes and ketones? Check this out. Both of these reactions you see here, the Clemmensen and the Wolff-Kishner, they do the exact same thing. They take that carbon-oxygen double bond, the carbonyl group, and they reduce it all the way down to a CH2 group, or a methylene group. The result is identical. So, how on earth do you choose which one to use? Well, this brings us to one of the most important concepts in all of chemical synthesis. The conditions matter. A lot. The Clemmensen reduction happens in a strong acid. The Wolff-Kishner happens in a strong base. So the choice is actually pretty simple. You just look at the rest of your molecule. Is there another part of it that might get destroyed by acid? Then you have to use Wolff-Kishner. Is it sensitive to base? Then you've got to go with Clemmensen. It's all about protecting your molecule. Whew, we have just gone through an entire workshop of chemical tools. So let's lay everything out on the workbench and put together a quick reference guide to help us organize everything we've just covered.
And here it is, the ultimate cheat sheet. This table really summarizes everything. Need to saturate a double bond? Easy, hydrogenation. Need to build a symmetrical alkane? You've got Wirtz or Kolbe. An asymmetrical one? Corey House is your best bet, hands down. And if you need to get rid of a carbonyl group, just check your conditions and choose between Clemmensen and Wolff-Kishner. This is it. This is the strategic thinking of a synthetic chemist, all laid out on one slide.
So when you get right down to it, the power to build molecules is really about knowing which tool to pick and when to pick it. From a simple addition to a complex coupling reaction, each one opens up a whole new world of possibilities. So the only real question left is, with this toolkit in your hand, what would you want to build?